welcome to 14.3. This is the one where we actually do partial derivatives. So here's a contour map of Mount Bates. And let's say that the height of Mount Bates is represented at any point by some function h of x and y. So I'm standing here on Mount Bates, here at point A, or point P, excuse me, where x is equal to A, y is equal to b. And I want to ask myself some questions about this. What happens if standing at that point, what happens if I walk in the positive x direction? Well, if I walk in the positive x direction, this way, if I walk in the positive x direction, I'm going to go to a higher contour in this case. So if I walk in the x direction, I'm going uphill. And those lines are fairly close together, so it is somewhat steep. If I walk in the positive y direction, on the other hand, you can see I'm actually going to go downhill. And it is much less steep. These are obviously just estimates. These are actually just kind of verbal things, so maybe I can actually do better. Maybe I can estimate it. So let's try to figure out what my slope is in the x direction. So if I want to estimate my slope in the x direction, if I walk in the x direction, well, I need to figure out how much my function changes over this distance, and we'll call this distance delta x. So how much does my slope change over this distance? Well, I've got to do the rise, so I'm going to do the height of a plus x, a plus delta x, because remember, I'm at AB, minus the height that I'm currently at. So that's the height that I would be if I walked in the x direction, minus the height that I'm currently at, all over, well, how far did I walk? Delta x. And this might start to look familiar. This is, of course, just an estimate. Obviously, it depends on the spacing of those lines. If I want to get even more accurate, I have to do the normal calculus thing, and I have to take the limit as that delta x approaches 0 of this same fraction h of a plus delta x comma b minus h of ab all over delta x. And if I take that limit, I get a derivative. That's just the limit definition of the derivative. But it's a little different. Notice that I'm holding b constant, and I'm only letting x change. And what we call this we call this a partial derivative, because there's two variables, x and y. So this is my partial derivative with respect to x. And notice when I take my partial derivative with respect to x, x changes and y stays constant. I could also do a partial derivative with respect to y, which of course would be the limit here as delta y approaches 0. If I have some, to the next contour line, call this distance delta y, of h of a comma b plus delta y minus where I currently am all over delta y, and that's of course the partial derivative with respect to y. Now we usually don't write out partial derivative with respect to y. We do have a better notation for this. There's actually a bunch of them. The equivalent of the dx, d whatever, is we actually write it like this. It's kind of a weird curvy d. It looks like a 2. Oops. Let's see, I put a d on the bottom. I'm a little out of partial h. That's just as a 2. Partial x. We could also write, let me write it a little cleaner, partial h, partial y. We'll also write these with a subscript sometimes. So you could write it as hx or as hy. Now there are other notations we will see. They use some other notations in our book. But we'll usually either use the partial over partial, or we'll just use a subscript for this. Now, you might ask yourself, how do we actually do a derivative? How do we actually do a derivative. And the way you do it actually is really suggested by the form here. So the way you actually do a partial derivative, is you take a normal derivative for the variable of interest. It could be x, it could be y, it could be whatever else. And all other variables you treat as constants. So let's take a little example here. And I'm going to give us a function. Let's take f of xy equals 3x squared y minus 2x plus y squared. So here's our function. And let's say we want to take some partial derivatives of this. So if I take an x derivative, fx, well, in this case, I want to just take a derivative with respect to x, and whenever I meet a y, I'm going to pretend that the y is just some constant number. So here I've got 3x squared y. Well, I see an x squared, I know I need to take a derivative of it, and it's multiplied by a y, but the y might as well just be a 2 or a 5 or some other number. So I'm just going to leave the y alone in this case. So I get 6xy. I see a minus 2x, that becomes a minus 2. And in this case, the plus y squared becomes 0, because what's the derivative of y with respect to x? Well, when I change x, y doesn't change at all. So that y squared term just vanishes. Similarly, if I take a y derivative, I'm going to see 3x squared times a y. That's a bunch of stuff times y. So this just becomes 3x squared. The 2x becomes 0 plus 2y. Now you might ask yourself, can I take second derivatives? And the answer is, you can take second derivatives. You can take second partial derivatives. So let's look here at what fxx is. So this is with respect to x, and then with respect to x again. Now obviously you get some more choices. So if I take my partial with respect to x and take a second derivative with respect to x, I get just 6y. And if I take my fy and I take another derivative with respect to y, well, I just get 2. Now, a funny thing's about to happen here. What happens if I mix my partials? What if I take my partial derivative with respect to x, and then I take a y derivative of it? Okay, well, 6xy, there I see a y, so this is going to become 6x. The minus 2 goes away. fyx. These are sometimes referred to as the mixed partials, by the way, because they contain different x then y or y then x. So if I do fyx, okay, well, 3x squared becomes 6x, and the 2y goes away. And you might notice a funny thing here, that the mixed partials, fxy and fyx, are the same. This is not an accident. This is, in fact, an example of something we will refer to a lot in this class called Clairaut's theorem. I have to make sure I spell this right. Clairaut's theorem. And Clairaut's theorem says, for any well-behaved function, and here by well-behaved, we mean that it's continuous and has continuous, and it has continuous derivatives. In that case, if we meet these conditions, what we find is our mixed partials don't care about the order, that fxy equals fyx. And it doesn't matter even if you go to like third derivatives and stuff, if they exist. If I had, fxxy, that would be equal to fxyx equal to fyxx. Doesn't matter. I can take my derivatives in whatever order I want, And as long as, I'm doing two x's and a y, for instance, as long as I'm doing the same derivatives, the order does not matter. So Clairaut's theorem really does help us out. The last thing that I want to point out before we do some more examples, some examples and kind of talk about the interpretation here, is you can also do functions of more than two variables. Excuse me. So I could have like f of x, y, z, x squared plus y squared plus z squared minus, I don't know, zy squared. And I could, it really doesn't matter. Fx, 2x, fy is 2y minus 2yz. Fz equals 2z minus y squared. And again, the same principles apply. No matter how many variables you have, 3, 4, 5, 6, 10, what you do is you take a derivative as normal with the variable you care about, and everything else is treated as a constant. All right, so let's investigate what a partial derivative is and what it means through the lens of a particular function. So here our function is 4 minus x squared minus y squared. And its partial derivatives are fairly easy to calculate. The 4 doesn't really matter. We get negative 2x, and we get negative 2y. And let's say we're at the point 1 comma 0, so x equals 1, y equals 0. A couple things become true, right? The value of our function is 4 minus 1, or 3. Fx at this point is, I guess, negative 2. And fy is 0. So what the heck does this mean? Well, let's go back to thinking about what a derivative is, right? So the first thing that a derivative is, it is the rate of change of f at that point in the specified direction. So what this tells me, think about our Mount Bates example, is that if I'm at 1, 0, and I move in the positive x direction, well, my derivative is negative, I should go downhill. And it also tells me that if I move in the positive y direction, it should be locally flat. Flalt. I can't spell apparently. It should be locally flat. It should be locally flat. So that's one thing that it means. Obviously, there's also a tangent line interpretation. So let's dive a little deeper, and let's start by looking at fx. So remember what a partial derivative means. It means that you change one thing, change one variable, hold the rest constant. So if I'm taking a derivative with respect to x, that means I'm only allowing x to change, and I'm fixing y. And in this case, I'm fixing y at the value of 0. So I'm actually going to imagine slicing this paraboloid with a plane that looks like y equals 0. So if I do that, if I take this slice, what I end up with, if you imagine slicing the paraboloid, is I get this little wedge. I guess it's actually even, if I continued it backwards, it would even be you'd see a full parabolic cross-section to the slice. So I'm kind of slicing it this way, and I get a little parabolic cross-section. And what this says is that the partial derivative is the slope of the tangent line to that slice. So I'm holding y constant, and now I'm allowing x to change. And what I'm saying is that my tangent line to that slice at that point should look like this. And what you notice is that as I move in the positive x direction, I go downhill, hence the negative slope. And you could even imagine, look, it varies as a function of x. If I took a point, if I went out a little further in x, I would even get a steeper negative slope. So when I'm slicing it this way, holding y constant, and now as I move along this curve, as I move along that parabolic curve, that cross-section, only x is changing, y is staying the same. If I instead think about the y derivative, what I'm doing is I'm going to slice it at a constant x value. So I'm actually going to slice it with the plane x equals 1. And so if I imagine slicing it with that plane, what I'm going to get out of that, if I slice a parabola, I'm going to get another parabola. So you could imagine that I've sliced it open. Let me see if I can even draw this. I've got kind of a flat face here with the bigger paraboloid behind it. I've lopped off the front face of it. And now I'm asking, at that point, what's my derivative? What's my tangent line look like in the y direction? Well, you'll notice I'm actually right at the peak. I'm right at the peak here. And so my tangent line in the y direction is actually going to be perfectly flat. So, which explains, again, why I get an Fy of 0. Now, if I move off in the positive y direction, this tells me I get a negative slope. If I move off in the negative y direction, I get a positive slope. So that sort of makes some sense there. So what the partial derivatives tell us is that if I'm standing at that point, 1, 0, what are my slopes as I walk in different directions? It's telling me that in the x direction, I'm walking downhill, and that in the y direction, I'm actually at a local little peak. That walking in the y direction, I'm not going to go uphill. I mean, kind of both ways are downhill, if you like. I'm about as high as I can get at this point walking in the y direction.